Hi, everyone. Great to see some of you. So the goal for the next almost hour or so is to give you an idea how to access FlyWire's data using programmatic tools, mainly the Cave client. I will also talk a little bit about how to download the segmentation data and the mesh data. I know some of you asked about how to access the meshes, and I'll point you to some places where you can, libraries that you can use to render those out. I will start with giving a background, just to cover some points that are important for the access, and I hope throughout this you will get an intuition about the data. Every data set has some quirks, some specifics, and I hope to cover these. Please use the Q&A. I will stop in certain places and try to address some of these. Also, feel free at those to unmute yourself and ask questions directly. All right, starting from the beginning, of course, FlyWire is based on an electron microscopy data set. That data set has an extremely high resolution. It's a 4x4x40 nanometer data set acquired by Sheng et al. And David Box lab. And using that, the Sang lab segmented the entire data set, meaning every voxel, every 3D pixel in this data set is assigned a segment ID. This automated segmentation was the starting point, and as many of you are probably aware, proofreading was necessary to correct errors in the automated segmentation to create neurons that are analyzable. And we have a set of about 130,000 of these neurons that are in this data set. And the first thing I want to highlight is that every segment has what we call a root ID. So you will see in this data set this word root ID coming up all the time. You can think of this as a segment ID, and if you're looking at a neuron or a cell, you can think of this as a cell ID. However, the other important thing to keep in mind with these IDs is that they describe a snapshot of a neuron. As proofreading progresses, somebody might make changes to a neuron, and the ID will change with it. So every snapshot of a neuron has a different ID. This allows us to show the data at any point in time, but it means that these IDs are not stable identifiers throughout time. Now, you will be analyzing a specific snapshot, so this is less relevant, but we will also release new versions, as I will show later, and IDs will change. There are mappings that you can use to basically see all the IDs for a given neuron, but I want to make sure you are aware of that. So FlyWire has seen almost 3 million edits through its history. I want to also mention that this is a data set in itself. So if you're interested in doing automated proofreading, for instance, this data set, I'd be happy to share, and please reach out about that. The other important thing to cover with proofreading is that we proofread the data set by going basically from the largest segments to the smallest segments. But we stopped at a certain point because some things are just too small to actually cover, and that is very similar to the hemibrain data set, how that was proofread. The consequence of that is that not everything in this data set has been proofread. So there are segments in there that are too small, or that are not a neuron, they are trachea, they are glia, or any other thing. Those things have not necessarily been proofread. And one thing specifically in this version is that not all photoreceptors actually were proofread. Initially didn't think they were proofreadable. They are, with a lot of work. And there will be a new version that includes all the photoreceptors. And then the consequence of that is that when you look at what we call a completion rate, so how many synapses are attached to a pre or post synaptic segment, meaning you have a synapse, it is connected to something on the pre side or on the post side. How many synapses are successfully attached as a percentage for each individual neuropil? What we see is that we have high completion rates on the presynaptic side and about a 40% completion rate on the postsynaptic side. So that is also in line with the hemibrain, and it is basically meaning that these tiny twigs that are at the neurons where they receive the synapses, many of them have not been attached. That is not an issue when you consider that connections in the fly brain are usually have many synapses, 5 or more. But keep in mind that when you look at the data, that some partners will not have been proven. We will see that later. Okay, so that is another part. Now synapses. We proofread the data set, but we also want to know all the synapses within it. We use synapses that were automatically classified by a group at Genelia, the paper Boomer et al. They basically went and every synapse with all its postsynaptic partners, they put in these linkers. So every individual, so we call a synapse a combination of a pre and postsynaptic site. So a presynaptic terminal may have many, many synapses. And each of these here is represented in the data set. What we do is we take these points, we take the neuron that is below it, and this allows us to track the synapse through time as the identity, the root ID changes, and we can assign the synapse to the correct root ID. So what you will see is that every annotation has also a point associated with it, and a synapse will have 2 points associated with it, a pre-point and a post-point. And each of these points then also has a root ID. Okay, so CAVE is the system that is basically behind FlyWire, and CAVE's responsibility is to allow people to proofread and to annotate, and at the same time to also analyze the data. The main feed here is to allow that while everything is basically ongoing for this purpose here, for analysis, we have a snapshot of the data. And what CAVE basically does, it versions the data at many snapshots in time. So as proofreading has progressed, these are all the edits that were made by the community. There were snapshots created throughout time, and version 6.30 is the one that we released and that you will be working with. I want to mention, though, is that the proofreading progressed since then a little bit, mainly to cover the photoreceptors and the outsides. And there will be a new version that is coming out hopefully in a month, that will be version 7.8.3, which also has those photoreceptors added to it. And so, yeah, what we will be covering is version 6.30. Okay, so and with that, with that, so there are 3 main ways to access the Connectome data. One, Amy mentioned already, that's codecs. There is the one that we will discuss now, the CAVE queries, but there is also, when you go to codecs, there's also a way to download data dumps. So when we go over here, there's download data. So this allows you to download basically a dump of different annotations, different statistics for all the neurons, for instance, here, and also SWC files, skeleton files are available as a dump download here as well. So this is one way to basically download data if you want to, especially if you want to analyze the whole connectome as a graph. This data is very useful. CAVE is especially useful when it comes to smaller sets of neurons, and you want to look at the annotations and the synapses, the individual synapses, and of course you can combine those to build the analysis that you are interested in. Okay, so what I will be doing is I have 2 notebooks that we will be going through. I will copy this in the chat, and I really hope you don't hear the leaf blowers that are outside of my apartment right now. Okay, so I will be posting this here in the chat. So the lower 2, these are Colab links. So you will be able to join these and follow along as I'm stepping through the notebook and showing you the results. But at that point, I want to ask, are there any questions to what I discussed so far? Okay, no questions. Oh yeah, Nick, you raised your hand. You can unmute yourself. Go ahead. Um, Nick, you raised your hand. Do you want to ask a question? Oh, I can hear you, buddy. Oh, we cannot hear you. You can also type your question in the Q&A or in the chat. Okay. Sorry about that, Nick. Yeah, feel free to ask a question in the Q&A. Okay, so let's head over to the Cave tutorial, and yeah, feel free to open that on your end as well and step through it alongside me. Yeah, so Cave has what we call the Cave client. The Cave client is kind of our door to anything Cave. It is a Python client, and you can use it in your collab or in your notebook locally. So this is just an import of multiple libraries that we were using this notebook. The first thing that you will need, even when accessing the public dataset, is is that you have to set up a token for your user. So if you run this cell on your laptop, which I will not do right now, is it will ask you to log in with a Google account, and then you will see a string, a token that you can post in here. Okay, Nick, I see your question. Let me briefly answer this. So yeah, we have two versions of skeletons. I will follow up with you. We have more high-res skeletons that we can make available. Okay, so everybody should be able to get the token if you want to follow along. Type it in here, and then you can store it locally, which will make future use easier. Or you can just pass it when you instantiate the client, and yeah, pass it. It will be passed in here and instantiate your client. I will take this out because I have a token locally. So the first thing to see here is that we instantiate the client with a data stack. A data stack is a combination of an EM data set, a segmentation, and a set of annotations. And if you would be using Cave with other data sets, for instance, a fancy data set, there would be a different data stack that would be put in here, and then you have access to all the data that is associated with that. So this is how you would instantiate a client for different data sets. So the first thing to check out here is the versions. So as I said before, currently available is version 6.30 as a public release. Later, you will see here future versions as we add more releases to the dataset that might have that will have a little bit more proofreading and also maybe a few more annotations. And for all those versions, there is a timestamp associated with them. In this case here, this was 21st of March. So you can see what is the exact snapshot that's associated with this version. So in Cave, we have this materialized submodule. This is the main place where we will be going to analyze to get data for analysis. Materialization is what we call the combination of annotations and segmentation. And when you combine those two, that's a materialized data set. That's at least how we would call it. And we can look in here, and we have a couple of tables available to us. We have the hierarchical annotations that we will cover further on. We have nuclei, and we have a list of all the neurons that we call proofread. So we can now go and query all those tables. To query a table, you just use the query table interface, pass it the table name, and it will return to you a data frame, a pandas data frame, which yeah, looks like this. So as we covered before, there is always a position associated with an annotation. This is in this case a representative coordinate that we placed in the backbone of the neuron, ideally right in the middle between where it may branch out to more dendritic and more axonic portion. And this idea is the idea of this neuron at that point in time. There are about 128,000 of these neurons available to us. Another table that might be of interest is the nucleus table. The same thing here. You can just type in the table name, get the entire table. It has more entries. That is because this table also contains nuclei for glia cells, for instance, but it's an automatically generated table, so it will also include some false positives. And the important thing here is that every single one of those tables also has metadata attached with it, where the creator wrote about what they actually did there. So you can get a table metadata, and in this case, the description. And in this case here, there will be more details about the annotations, and that allows you to judge what this data actually is, how it was generated, and sometimes also the person to reach out to if you have any further questions. In this case, I also want to highlight that the nucleus table is, when you just look at all the metadata, also has a segmentation source attached to it. So this segmentation source you can actually also look at in Neuroglancer. You can also, so I pasted this here as another layer into Neuroglancer. You can access. It's not showing up now for me. Oh no, I have to set it as segmentation layer here. So these nuclei are also available as a data source to you, and they might even have meshes. So here, this is another data source. If you want to analyze the nucleus size, for instance, you see that sometimes there's an error. It's rare, but it happens. And so we have sizes for these available, and locations, meshes. If you want to analyze this kind of data, it is available to you. And the same way you will be able to download the segmentation data, you will be able also to download the segmentation data for the nuclei later. One very handy feature when pulling those tables is to use split positions. That's just because pandas can be very unwieldy for lists within cells. This allows you to split any position columns into 3 separate columns. That is very useful, and I use that all the time. Additionally, you can also say, give me this data, please, in a very specific resolution. And this is always in nanometers. So here in this case, this would return to you the data in micrometers. And yeah, that's not a useful thing to use here when querying tables. So the query interface for tables is the same across all tables. And the next one we will be looking at is the hierarchical annotations. So in this Schlegel et al. Paper, Greg Jeffers' group, they annotated all the neurons in the data set in multiple ways. First, they assigned a flow to it. That is this neuron carrying information into the brain, outside of the brain, or does it stay intrinsic? And then they assigned superclasses to it. Every neuron in this data set has the superclass. But then, as we follow this hierarchy to finer and finer types, fewer and fewer neurons will have such an annotation. In many cases, that's also just because none has been established yet. And we can query this data in the exact same way as we have queried those tables before. And the first thing to note when this table comes back is that this one has many more entries. And that is because the entire hierarchy is in this table. And there is a column called classification system, which is associated with the level of the hierarchy. So if we just check how many do we have for each level of the hierarchy, we see that we have for flow the same number as proof-read neurons, but as we go down in the hierarchy, we have fewer and fewer of those available to us. And here's another feature of this function that is very useful here. It allows you to filter any of those columns. So for instance, you could now we are adding a filter on the classification system. We only want to have all annotations that are associated with flow over here. And this will only again return to us a table with the same number of proof-read neurons, only containing the flow annotations. And you could do that for any other. You can even stack them. There's a filter in where you can say cell class and cell type only, please, and so on. So these filter functions filter equal, filter in, and filter out. So here I want to have anything but flow. These allow you to slice this table in different ways to only get the type of data that you actually want in the end. Okay, and then the last type of annotation that I want to create, capture here are the community annotations. So the community annotations, they are free-form annotations where FlyWire community members were able to put in anything that they wanted. It is not a clean type of annotation, and this makes it also challenging for programmatic use, but it can be very useful for exploratory use. Like if you have a neuron and you have no idea what it is, checking in here in this table may give you an idea what it could be, given what somebody else reported about it before. It is less useful, though, for matching for specific names that you might be looking for. So, but this is still a very useful table. This table is also in further use, and Codex actually has a more up-to-date version of it. Okay, I want to stop before talking about synapses and see if there are any questions so far about what we covered here. I'll give you a second to catch up. Hey, so then finally synapses, which are, like one could argue, one of the most important annotations, but it is also one of the more trickier ones. And to give you a proper overview of that, I have to cover a little bit of background here. So the synapses that were automatically identified by Boomer et al., they identified about 244 million putative synapses. The problem with automatic detections is that they, of course, contain errors. That's something to keep in mind all the time. But in this particular case, there were many false positives within this data set. So Boomer et al. Themselves suggested to use certain scores that they added to filter down the data set. And there is a cleft score, which you only have to care about if you dig into deep into this data set, where we suggest a filter of 50, but you may find that you may want to set a different cleft score to get more synapses, but potentially also more false positive synapses. The other thing to keep in mind with this data set is that synapses that were, sometimes the synapse was annotated twice by their algorithm, and we then merged those together if they were within 100 nanometers and said this can only be one synapse really. So we kind of filtered down this table, and to make this conveniently available to you, there is unfortunately a different function which though acts just like the query table. It's called a query view. This here basically combines the Synapse table with a filter on top that allows you to get the data just as it was used in the release. And this table here, we create, I just get 10 synapses. It contains a pre-ID. Again, it's a root ID, but here pre-point root ID, we have a post ID, and then we have a lot of other features within here. So these features are first, neurotransmitter scores. They were also assigned by an automated method, in this case, Action et al., also in the Jan Funke's lab. Again, keep in mind, it's an automated method. We find it to be very useful when aggregating synapses within a neuron, but individual predictions might be less trustworthy. Also, we know that some neurons are co-transmitting multiple neurotransmitters, and that is not captured right now if you, of course, take the mean across a neuron. And that is definitely an area of more research to capture that properly. Then every synapse is assigned to a neuropil. So we have neuropil meshes. A synapse is assigned to the neuropil that's within. If it is just outside, we also assigned it to a neuropil. And lastly, we have specific locations, and these are nanometers for each and every synapse. So there are, in the end, about 120 million, I believe, synapses in this data set. And here we're now hitting the limit of what you can query. And if you would ask Cave to query the entire table, it will at some point come back to you and say, what you just tried to do is not a good idea. You asked me to query a lot of data, and we cap you at 500,000 rows. So this kind of incentivizes you to set filters for the neurons that you're actually interested in. It limits the impact on the database, but also it limits, it means that you don't run out of memory locally. So limit is one way to do that, but that's probably not the way you want to do for specific analyses. The way to do it would be to filter for individual neurons that you're interested in. So let's say we want to look at this neuron here, which is an AMMC A1. This neuron here, and now let's get all the synapses for it. So here, we have to do this now 2 times, because first we want to match on the presynaptic side this neuron. So we say filter in. In this case, you have to pass a list, because there could be multiple, and you could add all the AMMC and A1s in here, or all the neurons that you're interested in. And then you will get a data frame in return that only contains the synapses where this neuron is presynaptic. You can see here, it's always the same ID over here, but all the different IDs on the postsynaptic side. Yeah, so that's the first step. Again, you can see this neuron is mainly making synapses in the PVLP, AVLP, and the AMMC. Also noting those neuropils have site annotations alongside them. And on the postsynaptic side, we have, in this case, many more. But here we see that the post point ID is fixed, but the presynaptic ID, that is now changing. So I sometimes also get confused with what is pre and post, but yeah, we have to filter for the ID presynaptically. To get all the outputs of a neuron, we have to filter for the neuron postsynaptically to get all the inputs onto a neuron. So these data frames then allow you to do whatever analysis you want to do with them. You can, for instance, group by connection, so group by pre and post point root ID to get the number of connections that are onto a neuron, for instance, like so. Count is a good one. So, but yeah, but it's not a pre-planned analysis, but you would see here in this case we have 5 synapses that are coming from this one specific neuron here. Okay, so this is how to create a synapse table. And this, again, is for when you have groups of neurons in mind that you want to analyze. If you want to really analyze the entire synapse graph with all the 100 million synapses, the best place to go for that is to download the dump from Codex and work with that one directly. Okay, so I wanted to just give one example for how one can stack these now together to build an analysis. So here, we want to take one neuron. We will take the AMMC A1 again, and we want to see what are the superclasses, what are the identities of those neurons that are making synapses onto it, or that are receiving synapses from it. Identity in this case means superclass. So first, we will query our hierarchical annotations again. In this case, we will filter by superclass, so we only get the superclasses. And I will also, while added, also kind of extract the unique superclasses. As a recapture, we have central, ascending, descending, optic. These are only staying within the optic lobes, but they may actually also project between the two optic lobes. Visual projections, those that go from the optic lobes to the central brain. Sensory, those that come into the brain. Then motor, visual, centrifugal, those are from central back to optic. And endocrine, there are only 80 of those very specific neurons. And then what I'm doing here, this is just, there are multiple ways to go, but this is my favorite way. In this case, I just take the two columns that I'm interested in this superclass table. I'm only interested in root ID and cell type. I rename those to make my merging later easier. So in this case, I make a pre-version, a post-version of these by renaming those columns. And that allows me later to merge this more easily together with the Synapse table. This here is just a repeat from before. We're getting the synapses for this one specific root ID, pre and post-synaptically. And here we're merging them together. So what I'm doing is I take, for every synapse, I will now merge in the superclass of the associated partner. First, the ones that are targeted, and then the ones that will receive synapses. So one important thing to highlight, and that brings us back to the completion rates from before. When we look at those tables, those are a little bit smaller than the initial tables that we looked at before. So here we have 1700 and we have 256. And the reason for that is that pandas will just do an inner join with a merge, meaning that anything that doesn't have a match, it will just throw out. You can also do an outer join. The reason that this is happening, that stuff is getting lost, is because of the completion rate that I mentioned earlier. That for some partners, they were not proofread, and because they were not proofread fully, they're just very small segments. They don't have a superclass, and so they don't show up in your superclass table. That's how you may lose them. So this is why this table here is getting smaller in comparison to the table that we had up here. Okay, so this is not, it is just because of how the data is. You can make an outer join, but then you will, so you can tell pandas to do it this way, and then, oh, okay, in this, no, there's not a thing happening when we do outer join that I don't want to cover, but yeah, so this is, but coming back to this is the reason why this table is smaller. Okay, so with this, we can just, plot out how many, do I not probably find this? There's an underscore missing here. So with that, we can just, count up how many synapses are from neurons that are called central, how many are from neurons that are called ascending, descending, and so on. And we can do this also on the postsynaptic side. So here we see that this neuron, this also makes sense, receives more input from ascending than from descending, and makes more output onto descending than ascending. That makes sense how those neurons work. One thing to keep in mind here is that this is a synapse count. Some connections can have many synapses. So one other way to go about this would be to look at how many connections are there instead of how many synapses are there. But that will depend on your specific analysis and the needs that you have there. Okay, so this was a run through of what I think are the most important features for how to pull the data and wrangle it a little bit with the Cave client. And yeah, I want to stop here and see if there are questions. Yeah. Okay, so question by Farzan. So the question is, what are the minimum and maximum for cleft score? Does a higher score mean more confidence in a true positive synapse? And roughly, how well does a threshold of 50 match manually annotated synapses? Good question. So the cleft score is between, so higher is better. Is between 0 and 128, I believe. We in the original FlyWire paper, the Nature Methods paper, we actually CJ went through 999 synapses and annotated them as true or false. We curved that out and we selected a threshold based on that. And I can post a plot later. I will add it to this presentation. It's basically very flat. So there is like, you will see that cleft score close to 0, very many false positives, and then there is a region where it doesn't really matter where you put that threshold. And yeah, we set it at 50. But there is some wiggle room, and it doesn't change the analysis or anything much in that area. Then another question, I'm wondering how to navigate to a single synapse in NeuralGlancer. Yeah, so the one thing, that's a very good question. The one thing to keep in mind with individual synapses, and I will highlight this with one example. So we have this pre-synapse table. We have these two neurons, and let's navigate to one of these. So the one thing to keep in mind is that this synapse here is in nanometers. And then I will just copy this down here for reasons you will see in a second. So when you go to NeuralGlancer over here, it will tell you that it's currently using a specific resolution. So in this case, this NeuralGlancer is using 1640. So if you want to navigate to the synapse, you have to adjust your location to that resolution. So in this case, we will divide this here by 1640. Oh, I didn't import NumPy. And so here, over here, oh, this was also, so this would get you to this very specific synapse. And so this is the synapse here with this T-bar. That's the one that we were looking at in this. So this here, with those vesicles and that T-bar, that is the synapse that was on top of our table. There are ways to generate NeuralGlancer links programmatically, where you can put in all your synapses as blobs, for instance. And I'm not covering this here, but I can, I will leave a pointer. I will add another tutorial for that and show how to do that. These are very useful. We use them a lot. We use it a lot for building tasks and actually visualizing the data that we're analyzing. Okay, then I think.
Sven,
yeah.
So then you also had a question in the chat.
Oh, yeah, thank you. Thank you. So let's see here. Yeah, Andrew is asking, how would I download all skeletons of a certain type of neuron, e.g. Kenyan cell? Yeah, so the skeletons are provided as a separate dump, and I will double check that, but we have high resolution skeletons available. Those were created by Philip Schlegel. So they will be available over here, but if those are only the core skeletons, I will make sure the high-res skeletons are also being made available. So what you would do is you would go into the annotation table. I think Kenyan cells are somewhat included in the hierarchical annotations under class. So here, Kenyan cell. Take this table. We can do this very quickly together. We can take this table. We can we can match on, you can either query it with this filter, or you can filter it post hoc. And this would, okay, I would have to look up exactly, Kenyan cell, small c. Nope. Okay, I would have to look up how they're called in here, but I believe this table, sorry?
I think these are a class. A class would be a Kenyan cell.
Yeah, but did they should be in here. Yeah, so because in this case, cell type is everything that is basically the tag is all cell type here. Okay, but there's a way to get the Kenyan cells out of this, and then you can go back to the SWC download and filter them out of here. And I will look up how to get the Kenyan cells specifically.
I just dropped into, if you want to get just the IDs, then you can download them directly from Codex with
Okay. Yeah. So yes, so this is I think the question programmatic, non-programmatic analysis, I don't think of this as exclusive either. So you can, it's always good to go between the two. So in this case here, so they're called Kenyan underscore cell. And so you could get them. Yeah, here they are. So they are 5,000 at least annotated. So you can get them this way. Their IDs, you can get them in Codex. You might also find that in Codex it's better to explore, and then you go, when you know what you're filtering for, you go back to Cave and use that filter, and then you can get them out of this skeleton dump basically, and yeah, go from there. That's how I would go about that.
Sven, I have a question about query view. So does function already filter the clef score over 50 and also merge the cell within 100 nanometer?
That is correct.
Okay, so if I want to do like slightly lower clef score, but also merging like cell synapses within 100 nanometer, then I have to do that manually?
Yeah, so that is correct. So the problem is that, so again, we merge synapses to synapse links together if they were between the exact same partners and the preset was within 100 nanometers. That is, in all cases that we looked at, a duplicate annotation, but it depends on the clef score, right? So if you load a clef score, there will be more of those mergers to be done. So this is a clef score, a specific thing to do basically in some ways. So that's, yeah, well, the long story short here is that if you want to have a lower clef score, you would have to redo the merging. I have a notebook for that. It's actually quite surprisingly quick to do. But yeah, you would have to redo the merging.
Okay,
yeah. Okay, so then with those questions answered, we have a little bit more time, and I wanted to capture something that also many of you asked about, which is segmentation and mesh access. And this is now the other notebook that I shared. Here, the very important thing is that we will be using Cloud Volume. Cloud Volume is a package that has been developed and maintained by Bill Silversmith and the Sang Lab. It has become foundational to connectomics almost, like a lot of people use it for accessing data that is stored on the cloud, especially volumetric data. It is a heavy dependency though, so install of it may take a second. But once you have it, this is really all that you need alongside the paths for the data. And here I want to highlight how those paths work. So if you are over in NeuroGlancer, and you see over here, this is the path that is being used by NeuroGlancer to access this data. Here, this is for the nucleus, it's a different path. And if you would go to the EM layer, this would be yet another different path. And they usually start with pre-computed. You may also see graphene in there. You may also see graphene in there. This is our proofreadable layer. But those work just as well. So you could also use a graphene layer within Cloud Volume. So once you have your path, all you have to do is you have to instantiate a Cloud Volume object. And the Cloud Volume, I have to first import. And the Cloud Volume object, it takes some other parameters. I suggest these here. HTTPS access is usually faster, and in some cases is required. And the first thing that this has is a bunch of metadata. For instance, it will tell you what resolution the data is that it will return to you. This is important because what you will get are voxels, and they don't have a resolution per se. So this is important to know to match that to, for instance, the EM data. There's a bounding box that basically everything is within this bounding box, but a lot in this bounding box is also empty because of how the fly brain is shaped. You can use lower res data. Say you want to use the data very zoomed out. You can go what we call on higher MIP levels. They start at 0 and then they go up. Here we see that we are now at 64 nanometer resolution if you would go to that. So if you, depending on what the use case is, it might be beneficial to go to a higher MIP. And once you instantiate it, really Cloud Volume is almost like mimicking NumPy in how you can slice the data. So here I'm slicing out a data that has a block of 510 pixels. And these are my starting and end locations. Again, keep in mind, those are in 16 nanometer resolution. And so then I have this little function here. This is just because those IDs are so long, I use this here to remap them to IDs that I can assign colors to. And then all I'm doing here is visualizing one cut through this. And this is, yeah, what you would expect. This is just like what NeuroGlancer looks like. Just now you have everything in here, basically. And these IDs that are in the data, they will match the IDs that we just looked at in our cave tutorial, as long as you use the same version for them. This here is version 630, just as before. So the EM data works just the same. Yeah.
Can I just ask you, we have one question that came in from Nicole Guattari about if there is an annotation dictionary or sheet that shows all the definitions. So for instance, like how point position or point root ID, et cetera, are defined.
Yeah, so I can write a cheat sheet on these. There is not, but the way to see them is that every point PT is a point that defines the annotation, and it always comes with position and root ID. Position is the location, and root ID is the ID of that is below this point, and that is assigned to this annotation. And if they are multiple, they may have additional specifiers like pre or post. But yeah, I can add a little sheet that covers that. But we don't. I can't point to one right now. Okay, so then we have the EM layer. It works just the same as the segmentation. The one thing to keep in mind here is that you want to instantiate it on MIP 1 or higher. That has historic reasons, and when you do that, you will see that the resolution here is 8840, and that is because the segmentation was actually not performed at the highest available resolution. The segmentation was performed at the 1640, and the EM data is available in NeuroGlancer for 8840. And if you have a use case that requires that we also have 4440 available, it is not made available publicly. That is mainly because how much data it is, and because it's only located on premise in Princeton. But if you have a use case, please reach out. We're happy to share that with you. And so the one thing just to keep in mind is now we have a different resolution. So your coordinates here will differ from what you put in up there for the segmentation. And yeah, so you will see we can do the same thing. We can plot out a 2D screen. This is, for instance, also very useful to make figures if you want to show the EM, yeah, instead of screenshotting NeuroClancer. So that works as well. Okay, meshes. All right. First, I want to very briefly pause about segmentation and EM access. Maybe there are questions. I'm looking down here on my laptop. That's what I'm looking at, in case you're wondering. Okay, I don't see any question right now, but feel free to ask later as well. So mesh access. Cloud Volume can also give you access to meshes, and meshes can be addressed by IDs. So here I'm calling again the Cloud Volume segmentation object that we instantiated up on this notebook, and I'm calling mesh get with an ID. And you could call this with many meshes at once. That's why this is returning to you a dictionary, and I'm just grabbing out this one ID here. So if I would not do this, it will come back as a dictionary. So that's why I'm adding this here. So you can see this works very fast. It will return to you a mesh. The mesh has a large number of vertices, faces. You can store this. You can run this over all the IDs that you're interested in. You can store them as OBJs locally, or whatever format you're happy with, and you can use them to render them out. And I will say something about rendering in a second. The other feature of Cloud Volume is that, for this specific data, is that it has multiple levels of details. So if you want to plot a lot of neurons, thousands, you may run into issues with memory. You may want to access a lower level of detail. Multiple levels of details are available, and that depends on the neuron. But in this case here, we have a level of detail of 2 available to us. And I made a little mistake here. Oh yeah, so here's a comparison. So before, and the highest level of detail that we get by default, we had, that's almost 1 million vertices. Here in this lower level of detail, we have 230,000. So we saved ourselves about 4x the data for rendering or analysis, depending on what you want to do with meshes themselves. And yeah, you can store them locally. And Mesh Party is a package that we have developed on top of Cloud Volume. It handles some convenience functions. It has some caching. It makes local storage more easier. It's a whole thing itself that I won't cover, but I want to point you to it. It has a decent documentation, and it can do all this loading just as well. And here I demonstrate the caching effect, that once you load it once, it has it available locally. So you don't, if you want to load it multiple times, you don't have to download it again. And I want to highlight that it has a lot of features available to render meshes. It can make videos of meshes. Forrest Coleman has done a lot of work. This is a cortical cell. You can see this video was made with Mesh Party rendering. And if you look into the FlyWire paper, the one on bioRxiv, a lot of the renders in figures 4 to 7, they were made with Mesh Party. And you can do this programmatically. You can rerun it. You can set the camera and all that. So it's, once you get to know it, it's a very useful tool to build visuals that you can use. Okay, so we actually got everything on time, but there's still time for questions if you have.
There's one more question submitted by Nick. I noticed the mesh object you pulled says it has 0 normals. Is that typical? And a follow-up is, can't this cause issues with skeletonization?
So that is interesting. So I'm not sure why it says normals 0. We don't have usually don't have issues with normals, but normals can be funny. Yeah, okay, it's a good question. I have not noticed that. I would have to ask Will why in this specific case it has 0 normals. So for skeletonization, so skeletons were indeed created by actually skeletonizing the mesh, or the high resolution skeletons that you will get. Philip created them this way, and Mesh Party also has a skeleton feature where it can skeletonize a mesh for you. I don't think that there is we have not run into issues with that yet, but it's a good observation, and I will follow up with Bill on that. Okay, another question by Farsan. Is it possible to download a mesh of neurons and neuropil together? So you can download the meshes of neuropils, and they act in the exact same way. So you can, you can use this. The ID of the meshes is, okay, I will add a notebook that covers downloading and accessing neuropil meshes, but in the end, they act just as any other mesh. So you would have not 1 but 2 meshes, and you can render them together if you want to do so in Mesh Party. And I'm doing that with different alpha settings, so you can see both where they overlap, but they will be separate meshes. Okay, there's another question. Oh, yeah. All right. So we're at time. We will make this available. I will add some information based on the questions that were asked. Thanks for asking questions and making this interactive. If there's anything you're unsure about or your data that is not available, please reach out. There's most likely a way. And yeah, as we're building this resource to make it most useful, if you have a question, there's a good chance that many others have the same question. So yeah, please reach out and ask. Yeah, and with that, I think it's a good time to end the session.